Have you ever watched a video in very low quality in which you could make it high definition? Or perhaps, have you ever found a monochromatic image you'd like to colorize, or found a background image with a resolution too low for your device? Then Autoencoders can probably help you. Welcome to this video on Autoencoders. If you have no idea what an autoencoder is, this video is for you. Please note that this video series is aimed towards beginners without much background in computer science nor math. Its goal is to make you discover advanced and cool concepts visually, and so I hope you will like it. So, what is an autoencoder? An autoencoder has two main parts, which are the encoder and the decoder. In the middle there is what is called the bottleneck. Each of the encoder and the decoder are artificial neural networks. If you don't know what an artificial neural network is, you can think of it as a black box which can modelize any function you'd like. This is particularly helpful when the function you want to modelize is rather difficult to make by hand. For example, designing a function which can recognize whether an image is a cat or a dog can be very difficult. So, the main idea of autoencoders is to modelize the function which does not change the input. This function is also known as the identity function. But the identity function is not very interesting by itself. What's interesting about autoencoders is the content of it, and specifically the bottleneck. By now, you might have noticed the hourglass shape of the autoencoder. This hourglass shape accounts for the fact that as the input goes through the encoder, its dimension is reduced, and then when it goes through the decoder, its dimension is scaled up again. This means that the information contained in the input is compressed by the encoder to fit into the bottleneck, and then the decoder tries to read the compressed information and rebuild the original input. In other words, if we manage to build this autoencoder, we can read the information in the bottleneck, also known as the latent space, and get a compressed representation of our input. This can be very interesting for many applications. Let's see some of them. The first application that might come to your mind is compression. Let's say I want to send a big image to a friend on the internet, but I have a bad connection. Provided that my friend and I both have the same autoencoder, what I can do is use the encoder part to reduce the size of the image I want to send. Then I send this to my friend on the internet, and he can use the decoder part of our autoencoder to try and retrieve the image I encoded. This is the main idea behind compression. If you ever looked at your image files on your computer, you might have noticed at the end of the name of the files a .png or a .jpeg extension. In fact, JPEG is a compression algorithm that is very standard on the internet and which is used worldwide. So, every computer around the world has an algorithm which is able to decode JPEG so that you can read your image files. This way, when we want to share images, we don't have to share the whole information inside the image, but only some parts that are used to decode the image in the JPEG algorithm. In this compression example, the autoencoder would be a replacement for the JPEG algorithm. However, it is known that most of the time, handcrafted compression algorithms outperform autoencoders. This has to do with the way autoencoders are created, but I won't go into details here because it would be too technical. Another common application of autoencoders is denoising. A common issue faced by photographers when taking photos in low luminosity environment is that noise starts appearing in the images. This is due to the fact that when not enough light comes into a camera sensor, a random value may be captured by this photosite. This results in an overall low-quality image. But autoencoders can be used as a denoising technique which will remove the undesired random colors from the input image. So, how does that work? Remember when we said that as the input is going through the encoder, it is compressed into the bottleneck, right? Well, by definition, a compressed representation must be as small as possible, which means there is no place for useless information. Since noise is almost completely random, it cannot be compressed and so it cannot be taken into account in the bottleneck. So when we rebuild the image using the decoder part, the majority of the noise will have been removed. Before moving on to the next example, I'd like to dwell upon how autoencoders are built. In my previous example, the data which we used was only composed of images, but autoencoders don't only work with images. They can also be applied to any kind of major data. In other words, if the input is represented using a set of numbers, like a point's coordinates, then it can be used in autoencoders. This type of data is also known as Euclidean, in reference to the famous Greek mathematician Euclid. While I like to present autoencoders applications with images so that you can directly see what's going on, remember that it's not the only way you can use them. With that said, let's clarify a bit the design process of autoencoders. Since autoencoders are composed of artificial neural networks, they have to go through what's called the training process. This training process is specific to the desired application of the autoencoder and requires many input examples. For instance, if you want to build an image denoising autoencoder for images of paintings, the training process would require you feed many painting images to the autoencoder. This training process is the reason why autoencoders are data specific, which can be seen as a drawback. But it's also the reason why they can perform so well on this specific kind of data. To do so, they use the knowledge which has been accumulated during the training process about this type of data. If you want to learn more about artificial neural networks and their training process, feel free to have a look at the resources in the video's description. Let's have a look at a few more application examples of autoencoders. Super resolution is a task which consists in increasing the resolution of an image while trying to get the best quality possible. Autoencoders perform very well in this domain, and this application is my personal favorite. In order to achieve super resolution with autoencoders, we must shift their design by a bit. Instead of sticking with an hourglass shape, we'll build a trumpet-shaped one. Basically, if you want to make an autoencoder capable of doubling the resolution of an image, you'll make the output dimension twice as big as the input. For the training process, we usually take a high-definition image, artificially divides its resolution by the upscaling factor, and then we feed it to the autoencoder while trying to get the original image. We can then measure the performance of the autoencoder by measuring how close the reconstructed output is from the original image. Similarly to super resolution, you can color images with autoencoders. To do so, the architecture of the autoencoder must be like super resolution but with an upscaling factor of 3. But why is it exactly 3? It's because of the way images are represented in computers. Let's say you take an uncompressed monochromatic image. Its representation in a computer is actually a grid of values corresponding to the intensity of each pixel in the image. So, a 500 x 500 image would be represented by a 500 x 500 grid containing values ranging from 0 to 255. But color images need 3 times as much grids, because colors are represented using red, green and blue intensities mixed together in each pixel. So, if the output is of the same dimension of the input, but with 3 channels instead of 1, you'll get a color image instead of a monochromatic one. And for the training process, we can artificially transform a color image into shades of gray and try to retrieve the original color image. There are many other applications to autoencoders, such as watermark removal, image inpainting, or anomaly detection, as in credit card fraud detection systems. And since autoencoders are so flexible by nature, you can always invent a new way of using them. I hope you enjoyed this video and that it gave you a cool overview of what autoencoders can do. If you are interested about the technical details around autoencoders, or if you want to learn more about them, feel free to have a look at the resources in the video's description. This was my first video, so any feedback is welcomed. See you next time!